In this video tutorial, we're going to look at some of the computational problem-solving processes and applications that are available to engineers. Now, before we do that, we're going to answer two questions. First of all, we're going to answer the question, what computational problem-solving applications are available? And secondly, how are problems defined and processed using these techniques? So in the previous video, we introduced finite element analysis, and we talked about how finite element analysis can be used to look at things such as stress distribution, deflection of components under load, and various other different aspects of a design. Another important application that's associated with that is material selection. If, for example, we know where our principal stresses are and we know the magnitudes of those stresses, we can choose materials that are able to accommodate those stresses whilst incorporating a safety factor. So here we have a couple of examples of finite element analysis models. On the left-hand side we have a hook. Now this hook has a load applied down here at the bottom, but what we also notice is that we have stresses at the centre of this hole. Now the likelihood is that there's a chain or a cable passing through here, and the load that we're carrying is cylindrical, or it may be a support that's used to lift a different object. It could even be another hook or an eyelet or something similar. But the important things here are what the results are showing us. First of all, we're seeing where the greatest stresses are at the top of this hole here, and we've also got significant stresses on the inside and outside surfaces of the hook due to bending. We can see that we have stresses ranging from 0 megapascals at the tip of the hook, all the way to 18.5 megapascals at the top of the hole here. Now on the right hand side we have another model. And in this example here, we see the maximum stresses occurring at the webbing here on our support. Now the likelihood is that the back surface is fixed and a load is being applied through this hole. But once again, we see where the principal stresses are arising in this component. What we could do if the stresses that are occurring here and here are too high is we can redesign that component in order to reduce the stresses. Alternatively, we can select a material based around those stresses, knowing that it's going to be able to carry the required loads. Now, the other computer-aided engineering technique that we discussed was Computational Fluid Dynamics, and this can be used to not only look at fluid flows, but we can also carry out thermal analysis with CFD. Here we have a nice example of a fluid flowing through a globe valve, and we see on the left-hand side, as the fluid enters the valve, we have nice laminar flow. As the flow approaches the valve, we see that the fluid velocity increases, and at the exit to the valve we see a certain amount of turbulence. In the image below, we either have the valve open further, or this example here is taken at a different time interval, as we can see that the fluid velocity exiting the valve is greater in the second diagram. We can get various information from this about fluid velocities, fluid pressures and so on, and that may enable us to optimise the design of this particular valve. Here we have another example of the use of CFD, and here we're looking at flow across an aerofoil at different angles of attack. So if you can imagine, the airflow will be travelling from left to right and travelling across this aerofoil. In the first diagram we see a small increase in pressure at the leading edge of the aerofoil, but as a result of the angle of the aerofoil and its profile, we don't see any pressure variations above and below. This is what we would call a stalled position, because this aerofoil isn't going to cause any lift. As we begin to increase the angle of attack, what we see is higher pressure below the aerofoil and lower pressure above the aerofoil. Now, as you can imagine, this is going to generate something called lift, which is an aerodynamic force acting upwards as a result of those pressure differences. In the last diagram, we see the angle of attack has been increased to 20 degrees, and hence we see greater pressure variations above and below the aerofoil. If we didn't have CFD at our disposal here, then this would have to have been conducted in a wind tunnel, which may be more time consuming and also potentially more expensive. Now what we're looking at here is a very complicated model. This is a thermal analysis of a data center. So what we have is lots of servers generating heat, and we need to determine whether that heat can be dissipated or whether the equipment can be kept at a suitable temperature. Once again, it's a complicated model, but it'd be relatively difficult to replicate that without the use of CFD modeling. So this brings us on to how these types of problems are defined and processed. We're going to look at three key elements. We're going to look at something called mesh density, we're going to look at boundary conditions, and then we're going to discuss something called the iteration process. So first of all, mesh density. What this diagram highlights quite nicely is we can take the same component and we can apply different mesh densities. Now, the important thing about meshes and mesh density is that each of these nodal points, so the points where the mesh elements meet, the simulation software is going to carry out a calculation. So at every single one of these nodal points, a calculation is going to be done in order to determine how the stress is distributed on this component. Now, I'm sure you can appreciate if we move to the second diagram, we have more nodal points. That means there's more calculations to be done, and hence the computation time is going to be increased. The software is essentially calculating the stress at every single one of these nodal points and giving us a stress distribution as a result. We see in the third image, we have a much more refined mesh with lots more nodal points. So on first inspection, you may draw the conclusion that a coarser or larger mesh is better, but there's other aspects to consider. If we take a look at this diagram here on the left-hand side, we see a component with a coarse mesh applied. Now, this section of the component in the bottom left-hand corner is circular, but the computer software doesn't see the object. What the computer software sees is the mesh. Therefore, if we have a coarse mesh applied to the outside of the circle, what we end up actually seeing is potentially an 8 or 10-sided shape. So it doesn't necessarily accurately represent the component. Now, if, for example, the principal stresses were occurring at that surface, then we would need to carry out a lot more calculations at that surface to make sure we've pinpointed and determined the maximum stress. So as we move from left to right, we see that the mesh, particularly on this surface edge, is being refined. So we end up with a more refined mesh on that surface, and what that enables us to do, first of all, is to have a finer mesh at the section of primary interest, but we can then have a coarser mesh where we know the stresses are less and we have less interest. So we can refine the mesh in this way in order to reduce computation time whilst still achieving accurate results. And here we see another example similar to the previous example where we can see that our principal stresses are occurring on that curved surface, but it's very difficult to pinpoint what's happening elsewhere along that surface. By the time we get to the diagram in the bottom right hand corner, we can gain a much better understanding of what's happening on that surface. So next, it's important to consider something called boundary conditions. Now, if we didn't have access to computer-aided engineering techniques, then our boundary conditions are essentially the inputs to any stress-strain calculation. We would know the force, we would know the cross-section, we would know which components were constrained. Now that's a very simplified way of considering boundary conditions, but what we have to do is we have to tell the computational model what's fixed, where forces are applied, how mating surfaces are relating, and so on. And I'll give you a few examples of this. We said previously that we'd have a cable or a chain passing through the hook here. What we would need to tell the software is whether the chain and hook were capable of moving independently of each other. So could this hook swing in theory? Or are the two components mated together with a fixed connection? Again, is our load free to move? Are these two surfaces mated together, or is this load free to roll from side to side? There'll be lots of other boundary conditions that we could apply, but this is really just to give you an understanding of the importance of defining boundary conditions as accurately as possible. Now, the same is true for our example on the right-hand side. Let's disregard what's happening on the back of this bracket for the time being and concentrate on what's happening at the hull. When we define how this load is applied, we need to consider a couple of things. First of all, do we have a point load or do we have a distributed load? How is the load connected through this hull? If it's being connected by a bolt or rivet or similar, how large is the head of that bolt? So how is the force distributed across this top surface? The more accurately we can define our boundary conditions, the more accurate the results we generate as a result. And again, if we come to our complex thermal analysis, there's lots of things happening in this example because we've obviously got heat being generated by the servers, but we've got temperatures of our outside walls, we've got temperatures of the ambient air, there's going to be convection currents as a result of temperature variations, which is going to cause convection. So we'd also need to know what's causing any circulation of this air. Now once again, if we don't define those boundary conditions accurately, then the issue we face is that we won't have confidence in the results that we generate. Now particularly with thermal problems, we have surface heat transfer coefficients, so between the server casing and the air, and we also have different types of convection, so we'd need to define that problem as accurately as possible. Now the final thing that I want to mention is the iteration process. I mentioned earlier in this video, referring to our diagram on the right hand side, is that the software carries out a calculation at every single one of these nodal points based on the boundary conditions that we apply. So the only things that this software knows is that a force is being applied at this hole and the back of this bracket is fixed or inset in some way. So essentially what the software does is it produces a simultaneous equation for every single one of these nodes. So we have a node here next to the hole. The software package is going to look at what it knows about the forces applied at the hole, and it's going to generate a simultaneous equation based on that information and information for all of the surrounding nodes. Again, at the back of the bracket, we will know something about the fixings on the back of this plate. So at each of these nodal points, the software is going to look at the back of that plate and take what's known or defined and create a simultaneous equation for all surrounding points. So, as an example, we might end up with hundreds or thousands of simultaneous equations, which are difficult to solve. And what the software does is it assigns arbitrary values to each of these nodal points. And then what it does is it looks for solutions. It's kind of a trial and error process. So when we talk about the first iteration is going to be very inaccurate because arbitrary values are assigned to each of these nodal points, and then the computer software checks to see if those values that it assigned were correct. Obviously in the first iteration this wouldn't be the case, so it moves on to the second iteration and it makes a second approximation, and this approximation is going to be more accurate than the first because it already has some information about those systems of equations. So what the software does is it continues to do this trial and error process until we get something called convergence. Now convergence is when on subsequent iterations the results from the previous iteration and the new iteration are almost identical. Once we get to that point, we know that we're getting very close to the final solution. So first iteration provides a rough approximation, second iteration is more accurate, third more accurate, and so on, and the software is going to look until two subsequent iterations have results that are almost identical, and then we know that we've achieved the final solution. That's what we mean by the iteration process and convergence in our calculations. So just to summarise, in this video we've looked at some of the computational problem-solving processes and applications that are available to engineers. We've also discussed how these problems can be defined and processed. So what we're going to do in the next video is we're going to come up with one of these models or approximations, and we're going to carry out some simulations or some calculations until we achieve convergence. We're going to use Excel for this so that you can see how this process works within the computer-aided engineering software itself.